On slide 49, we turn to the key topic of having not only distal outcomes, but also covariates with missing data, a very common situation that we'll take our time discussing in some detail with different approaches. Slide 50 shows the model that we're going to consider. We still have the 6 latent classy indicators. We have the 3 distal outcome variables that we looked at a little bit earlier. And now we add 3 covariates X. Again, the latent classy indicators are binary. The distal outcomes is a mix of continuous and categorical with missing data. And now what's new is the covariates, where X1 is binary, common feature, and X2 and X3 are continuous, and we have missing data on X1 and X2. And importantly here, the slopes in the regressions of Y on X are not class varying. And that's important for understanding the effect of C on Y. So effect of C on Y is seen in the class varying Y-intercept and thresholds, but that's only the case when the regression slopes of Y on X are not class varying. In the further topic section, we discuss class varying Y on X, so class varying slopes as well, but that's not the case here now. Slide 51 takes a look at the Monte Carlo generated data. That's the distal.dat data set again, and where the sample size is 1000 and the entropy is 0.74, moderate entropy. And in the output, you will see that we have missing data on the covariance shown by the covariance coverage output. So for the 3 axes, we have the coverage, univariate coverage, and the bivariate coverage. So for instance, for X1, 81% of the sample is observed, which means that 19% is missing, and that's the same thing for X1 and X2. Now, in line with the regression analysis, individuals with missing on one or more of the covariates are deleted in the analysis with covariates when you don't take into account the missing data. And then the sample size drops from 1000 to 668, which is a 33% loss, pretty big loss. 0.668 is the same as this number here, where that's the case where X1 and X2 are both observed. Now, X1 and X3 has no missing data. Now, so this loss can be avoided, as we say here, by bringing the covariates into the model, that is, estimating their marginal distribution by covarying them using the with statement, or alternatively by using multiple imputation. Slide 52 then. I'm talking through various kinds of approaches, manual multi-step approaches, which deals properly with missing data on X in the last step analysis. So you can bring the covariates into the model, or you can do multiple imputation. When you choose to bring the covariates into the model, you can use maximum likelihood and numerical integration, or you can use Bayes. With ML, you have the choice of 3-step, whereas BCH is not available with numerical integration, and 2-step. So 3-step and 2-step are available, not BCH. And the advantage here with the ML numerical integration is that you get likelihood ratio testing available. The negative part is that you cannot handle many covariates with missing because of the numerical integration getting too heavy. And the approach can be somewhat unstable with large amounts of missing data, and can be imprecise without adding many integration points. And finally, you cannot specify that you have categorical covariates, like the binary x1. The base approach is also available for 3-step and 2-step, but not available for BCH. Because base and weights don't go together. The advantage is that this is fairly stable analysis. It doesn't have the integration problems that ML has. And the negative aspect is that you don't get the likelihood ratio test, and computations can be slow, particularly with large samples. And that, again, you cannot specify categorical covariates. That's the same disadvantage as with ML. And finally, then, multiple imputation, where you have all three methods available. And the pro is that it's stable. You can specify categorical covariates, so x1 will be handled properly. And you can use non-model variables for missing data imputation. So you can bring in other variables with other information than what you have in the model variables. And the con is that you don't have the likelihood ratio test easily available, and it can be slow with many covariates with missing. Now, the one method that is available for all of these three different approaches is 3-step. So we're going to demonstrate 3-step here only, but as an exercise you can try 2-step, for instance, or BCH when you do multiple imputation. So where are we in the outline? Well, we're in the manual multi-step approach. We are dealing with distal outcomes and covariates with missing data, and now we're going to take a look at a first approach here, ML and integration using 3-step. So slide 54 then looks at the distal.dat that we generated, the one replication Monte Carlo generated data that we are working with. That's a variable list. And we're going to use the latent class indicators. That's what we always do in the first step. And they are categorical binary. Missing data is designated that way, 3 classes. And what we want to do now is to save variables for the last step. Then this is the new feature then that we have x1, x2, x3 here in addition to the distal outcomes. Otherwise, this is the same as it was for distal. Apart from the fact that now we save a data set called cprob_yx to differentiate it from cprob_y that we had before. But since we're dealing with 3-step, we're saving cprobs. So what we have here then is the save data. We save the U indicators, the x's and the y's, and cprob 1 through 3, and the most likely class. Slide 56. With 3-step, we need the logits. So these are the same logits as we had for the first step of slide 39, because it refers to the measurement model. First step is the same. Last step of 3-step with integration then, what do we have? Well, the data set we're working with is a cprob_yx.dat with the variables laid out this way, as we saw in the save data. And we're going to use x's and y's, because they're the ones we're interested in of the full model in the last step. But with 3-step, we also have the nominal variable, most likely class, that we call n here for simplicity. So that's declared as nominal. What's categorical? Well, y1 and y2 are. But we don't have the possibility of declaring x1 as categorical, despite the fact that it's binary, and that was a disadvantage of this method. 3 classes, estimator MLR, and starts equals 0 because we're in the last step. And now we have to specify algorithm equals integration. And we're going to have 2 dimensions of integration here due to missing data on x1 and x2. x3 doesn't have missing data. So you can see that when you have many x's with missing data, you're going to get many dimensions of integration. It's going to be very heavy computations. In this case, we have to use integration equals Monte Carlo. And as the comment says here, it's due to the partial missing x variables. So partial missing means that for some people, you don't have missing on x. So that's different from latent variables where every person has missing data. And that feature, the partial missingness, calls for Monte Carlo integration. The default is 500 points. With missing data on many axes, you may need more points. The input continues on slide 58, and where the key feature is that we covary the exits with each other here, and thereby bring them into the model. The disadvantage of that is that the binary x1 is treated as continuous normal, and we discussed that in detail in the statistical methodology section. It's not a big disadvantage, but it is an issue you should be aware of, and a problem or an issue that's avoided by multiple imputation. We have then the familiar fixing of the nominal most likely class variable at these different loaded values. So that's 3-step with integration. So then let's turn to the next manual approach, distal outcomes with covariates missing data, and we are on to base. So here we are for base. 3-step using base in the last step. No numerical integration needed. So the data set is still the cprob_yx because we're still doing a 3-step, albeit in a base framework. So we have the names list here from that data set, and we're going to use x's and y's, but also this nominal most likely class variable. And the estimator now is base, and we ask for a certain number of base iterations. At least 5,000 is what we're saying here. Start is 0 still because it's last step. Now turning to the model here then, it's the same as for ML with the integration. We bring in the axis using a with statement, and we have fixed the nominal n variable, most likely class variable, at the loaded values that we had before for ML, for the ML approach. So the new feature here really is the estimator base, and with base we usually want to monitor Tech8 to see that the base iterations go well and go down to PSR values close to 1. And in version 9 of Mplus, we've added another indicator of good convergence called effective sample size. And that is a useful feature. And I'm not going to talk about ESS right now. I'm going to only refer to a FAQ that we have or have on our website about that. That indicator or indication of convergence calls for close to 20,000 iterations for us to have a trustworthy solution, as opposed to the 5,000 that we start out with here. So you would have to rerun it with, say, 20,000. But that's okay. Slide 61 then, we turn to the third possibility, multiple imputation. And we're still going to stay with the 3-step approach. So multiple imputation it's generally not needed for missing data in the latent class indicators of the measurement model, or for missing data in the distal outcomes. The FIML approach is sufficient, using all available data. But multiple imputation is useful for missing data on covariates, because the imputation model can bring in variables related to missing data that are not in the model. So they bring variables that bring information that you don't have in the variables of the model. No numerical integration is required after the imputation because there's no longer any missing data after imputation. And we have all three methods available to us. Here's a good paper, a technical report, multiple imputation in Mplus, and with some practical advice for avoiding problems in the imputation. 17 general tips from our experience with difficulties for certain situations. So what does 3-step with multiple imputation look like? So we're considering the imputation step with data from the first step of 3-step. So the data set is cprob yx from the first step, and with that names list. And the use variables that we have here are the x's and the y's. These are the variables used in the basic analysis down here at the bottom to provide sample statistics, and they're also the variables that are saved in addition to the variables on the auxiliary list, which is the nominal n that we need, the most likely class variable that we need in the last step. So now we do the data imputation step here, and we have a name statement and an impute statement, and this is new to version 9 of Mplus. The imputations use information from the variables on the data imputation names list. So these are the variables that contribute information to imputing, and impute, that option, concerns imputing values for variables on that list. So we're imputing x1 and x2, but we draw on information from the use and from the from x3 and from y1, y2, and y3. And in parentheses here, we state whether a variable is categorical or not, binary or ordinal, both in how we use it for imputation and how we impute. So we impute that as a binary variable in that case. The names list must include all use variables. And in this case, we request 100 imputations with a thinning of 100. So we don't record every iteration, we record every 100th iteration to avoid autocorrelation between the draws. And we save that as an impute star.dat data set, which gives you all 100. So analysis is type goes basic, sample statistics use for the use variable computed after multiple imputation done by Bayes. Here you can specify the number of Bayesian iterations referring to the data imputation step, and you can monitor by Tech8. The computation that's done using type equals basic is done by WSMV, the WSMV estimator, after the imputation, computing the sample statistics for the use variables. On slide 64, I take a closer look at what's happening with the data imputation. In the Mplus output, you get specifications for the imputation. We see the number of imputed data sets that we asked for, and a default setting is activated, so-called H1 imputation. H1 referring to an unrestricted model in line with language of structural equation modeling, where you have H1 and H0. H0 can also be used for imputation, but here it's the unrestricted H1 model, and with the default covariance setting, which is described in the technical document for imputation that I mentioned. We use thinning with 100, and we have 12 dependent variables, 12 variables altogether, and 82 number of parameters. So what does this mean? Well, first of all, the number of variables and the H1 parameters are determined by data imputation names list. So the names list here, we have 6 U variables, 3 X variables, and 3 Y variables. So 12 all in all. And then you can figure out the number of H1 parameters. It's computed as follows. You look at the number of covariances or correlations. That is the off-diagonal element in a covariance matrix. 12 times 12 minus 1 divided by 2 is 66 parameters. And the number of means and variances, well, means and variances come about from continuous variables. And how many continuous variables do we have? Well, we have x2, x3, and y1. So we have 3 such variables. So 3 means, 3 variances, adding to 6. And then I claim that we have 10 thresholds. So what's that? Well, we have 6 binary ones. That is 6 thresholds. A 7th threshold for the binary x1. And an 8th threshold for the binary y2. And then for y3, we have 2 more thresholds because it is a 3-category ordinal variable. So that gives you a total of 10 thresholds. So you can see that when you have many variables, the number of H1 parameters can get quite large and sometimes prohibitive. So what's happening here is that we estimate this H1 model using Bayesian analysis. So in Bayesian analysis, the unknowns are not only the number of parameters, 82 in this case, but also the missing data. So we calculate missing data values in the Bayesian iterations. So as a side product of that step, that Bayesian step, we get not only the H1 parameters, but all of the missing data as well. So once the model has or rather the Bayesian analysis has converged, we draw 100 more draws in the MCMC, Markov chain Monte Carlo sequence, to get the imputed values for the missing data in the model. And then that is what we use to produce the imputed values for x1 and x2. We could also request the missing data for y1 and y2 if we wanted, but that's not what we're doing here. The save data information says that we're saving x's and y's and n as expected into a data file called imp_star.dat, which on slide 66 is expressed this way. So we're talking about the last step of 3-step after imputation. The file is then imp_list. So that's a file that lists all of the 100 data sets and points to them. And now the variable type here, or the data type rather, is type equals imputation. So type equals imputation data. And the variables are the ones we saved, and we use these variables in the analysis in the model over on the right, and the n is a nominal variable and the y1 and y2 are categorical, and missing is like before, 3 classes, starts equals 0 because it is the last step. And note then that we have not designated x1 as categorical, and that's for the following reason. Over here on the right in the model, we have C on x1 to x3 and y1 through y3 on x1 to x3. So the x's are all covariates, exogenous, independent, and therefore, since their x variables are independent, you don't have to specify the variable type. It's x1 is just a dummy variable. So that's one thing to note. And the other thing to note is that there is no x part, no x1, x3 with x1, x3, because we don't have to bring the x's into model because the x's no longer have missing data because we imputed for it. Otherwise, the model is the same as before for 3-step, the fixed nominal variables at the fixed loaded values.